Ciao, I'm Daniela.
And I'm Francesco.
And we are postdocs in the model group within the National Research Council of Italy within the Spin Institute, led by Silvia Picozzi, with Paolo Barone as permanent researcher, and Udai, who started his PhD this year. We are active in the atomic scale theory and modeling of material properties, materials which are exploited in various technological applications and devices. In particular, we investigate structural properties, electronic properties, dynamical properties, and magnetic properties. And we do that thanks to first principles calculations based on density functional theory. Our study can be then also supported by further analysis of symmetry and model Hamiltonian approaches, and complemented eventually with Monte Carlo-based simulations. But so, what is DFT? Well, DFT is a computational quantum mechanical modeling which allows to determine the ground state energetics and so the ground state properties of a multiparticle system at 0K temperature. This is because the DFT is based on the computation of the electron density. In fact, the fundamental of DFT is that any property of a multiparticle system is a function of the ground state density. The most known and used functional approximation then are the local density and generalized gradient approximation. And nowadays, DFT is successfully implemented in a huge variety and different codes and softwares. And so let's now see some example.
Okay, so one of the very basic things that people using DFT do is the structure optimization, which basically is a necessity because usually we start from simulating some approximated structure, and it means that we need to relax all the atomic position and all the total energy of the structure toward the global minimum. Now, as Daniela said, there are many different codes which are currently implemented to perform DFT calculation. I will show you the one that we are currently using in the modern group, which is VASP, which stands for Vienna Ab Initio Simulation Package. Okay, now to run any kind of simulation within VASP, you will basically always need 4 input files. The first one is called POSCAR, where you can find all the geometrical information regarding the structure that you are going to simulate. So, for instance, the primitive vectors and the atomic position, the atomic coordinates, which can be written in fractional coordinates or Cartesian. The second input file is the INCAR file, where it is written the kind of job that you are going to perform. And since we are going to perform some structure optimization simulation, here are included also the information about the algorithm that is going to be used and about the degrees of freedom that we are going to relax during the simulation. And then we have some information about the K-point match that we are going to use during this calculation, and about the pseudo-potential that is being used from the DFT code to represent the interaction between the nuclei and the electrons. Now, what you have to do in order to run the simulation is just to call the script of VASP, and you can see that it will print line by line the output. So you have some information, some initial information, some very general information about the simulation, and then you can see that it's reading the POSCAR and the INCAR file, and then you have step by step that the information from the self-consistent calculation is printed. Now we can quickly switch to the result of this kind of simulation that I previously computed, and all the information that you're going to need from the DFT calculation are summarized in the outcar file. So you can see again you have some very introductive information about the kind of simulation that you're going to perform, and you can also find information on each step of the self-consistent procedure, as you can see. Now, what we can do from the outcome is to collect all the global information, all the information that are produced during the simulation, and for instance, we can plot the trend of the total energy as a function of the step. So you can see that at the beginning we have these very, very efficient dynamics moving from the initial approximate configuration of the system, and then we are quickly moving toward the global minimum. And we can also plot the forces which are acting on each atom as a function of the simulation step. And again, you can see that we have these very efficient dynamic at the beginning of the simulation, and then the forces converge toward zero. What we can do, apart from visualizing these results, is to visualize all the relaxation, the evolution of the relaxation, and we can do it with a variety of different tools, from JMOL to Vesta. What I'm going to use now is called ASC, and is a tool from Python. So here you can see the initial configuration, and then you can play the animation. So you saw that there is this very, very efficient initial dynamics, and then there is this fine-tuning. And again,
beyond structural properties, we can also get information about lattice dynamical properties, for example, by performing phonon calculations. In fact, by doing this, we can predict structural frustration of a system, and so the possibility that this system could undergo to a structural phase transition. In fact, thanks to DFT, we can solve the dynamical equation, get information about phonon frequencies and associated eigendisplacement. And for instance, if you look at the case of barium titanate in its cubic phase, and we explore the phonon dispersion curves, we can see the appearance of different phonon instabilities, which corresponds to imaginary frequencies, that are associated to distortion, which breaks the special inversion symmetries and thus give rise to a dipole moment.
And indeed, as you can see from the picture, the total energy of the barium titanate primitive cell along the distortion is forming a double well shape, which is typically of certain ferroelectric transition. And this is telling us that the barium titanate cubic phase is unstable against the distortion toward the tetragonal polar phase. Now, to further characterize this phase transition, we focus on the electric properties of the evolution of the electric properties along the distortion, and specifically we can compute the macroscopic electric polarization. We can do it for each structure along the distortion, and you can see the green line represents the total polarization, which is given by the two contributions, the ionic contribution and the electronic contribution.
Beyond then the so-called ferroelectric properties, we can then also get information about magnetic properties like magnetic moments or a magnetic interaction parameter, which can help us to understand and identify magnetic ground state for a magnetic system, of course. And this, for example, can be done via energy mapping of various spin configuration. And moreover, we can achieve information on many other properties and their eventual interplay. And with that, we hope that we have shed light on the main features of density functional theory and unveiled a little bit the world of a DFT-based group. Bye!
Ciao!